Right now, at this very moment, while you sit comfortably watching this video, there is something out there. Something small, something fragile, something that weighs less than a compact car. And it is screaming through the void of space at 61,000 kilometers per hour. It has no engine running, no fuel burning, no pilot steering. It is just drifting. Silently, endlessly, through the coldest, darkest, most empty place you could ever imagine. It is farther from you right now than any object ever built by human hands. Farther than any satellite. Farther than any telescope. Farther than anything we have ever sent out into the universe. And here is the thing that should keep you awake tonight. It will never come back. It will never stop. It will keep moving through space for millions of years. For billions of years. Long after every city on Earth has crumbled to dust. Long after every ocean has evaporated. Long after every mountain has been worn flat by time. And long after our sun, the star that gave us life, that warmed our faces, that powered every civilization we have ever built, finally runs out of fuel, swells into a monstrous red giant, devours the inner planets, and collapses into a cold, dead white dwarf. Even then, this tiny spacecraft will still be out there, somewhere drifting, carrying a golden record that holds the sounds of Earth. Music, laughter, a baby crying. The sound of wind and thunder and waves crashing on a shore that no longer exists. The question is breathtakingly simple, but the answer will take us on the longest journey ever attempted by the human mind. Where will Voyager 1 be when the sun dies? Think about that for a moment. Really think about it. We are asking where a spacecraft launched in 1977 will be 5 billion years from now. We are asking a question that stretches across a span of time so vast that the entire history of human civilization, every empire, every war, every poem ever written, every child ever born, all of it combined represents less than 1/1,000,000th of the time we are about to explore. This is not just a question about a spacecraft. This is a question about time itself. About the fate of everything we have ever known. About whether anything we create can truly last forever. And I want you to come with me on this journey. Every step of the way. From right now, this very second, all the way to the death of our star. And beyond. I promise you this, by the end of this video, you will never look at the night sky the same way again. You will never think about time the same way. And you will understand something profound about what it means to be human in a universe that does not care whether we exist or not. But before we begin, I need you to do something for me. If the idea of tracking a tiny spacecraft across 5 billion years of cosmic time excites you, if the thought of understanding where humanity's farthest messenger will be when our sun breathes its last excites you, then hit that like button right now. Subscribe to this channel. And drop a comment below with your guess. How far do you think Voyager 1 will be when the sun finally dies? Write your answer in the comments. I will give you the real, scientifically calculated answer by the end of this video. And I promise you, the real answer is more mind-blowing than anything you could guess. Let us begin. I want to start with a story. A real story. A research story that happened very recently, and it is this story that inspired everything you are about to hear. In June of 2024, at Harvard University, one of the most brilliant astrophysicists of our time, Professor Avi Loeb, sat down with his undergraduate student, a young man named Shokhruz Kakharov. And Professor Loeb asked him what seemed like a simple question. He said, "Shokhruz, where will Voyager be in 1 billion years?" Now, you might think this is easy to calculate. You just take the speed, multiply by time, and get a distance. But no, it is not that simple at all. Because Voyager 1 is not traveling in a straight line through empty space. It is traveling through a galaxy with over 200 billion stars. A galaxy with vast clouds of gas and dust. A galaxy with a supermassive black hole at its center, pulling on everything within 100,000 light years. A galaxy where everything orbits, curves, rises and falls in complex gravitational paths. To truly answer where Voyager will be in 1 billion years, you need to model the entire mass distribution of the Milky Way. You need to account for dark matter halos, for the gravitational pull of spiral arms, for the subtle influence of neighboring dwarf galaxies. You need a supercomputer and months of calculations. And that is exactly what Shokhruz did. Using a detailed computational model of the Milky Way's mass distribution, he plotted the future orbit of Voyager, one relative to the Sun, over billions of years. And the result was stunning. Within 1 billion years, Voyager 1 will have drifted to the opposite side of the Milky Way disk relative to the Sun, 50,000 light-years away from where it started, on the other side of an entire galaxy. And here is what Professor Loeb noted with characteristic dry humor. He said, by the time Voyager reaches the other side of the galaxy, the Sun will have already boiled off all the oceans on Earth. NASA might not be around to celebrate this milestone. Those results are heading toward a peer-reviewed paper. Real science, real calculations. And they tell us something extraordinary about the journey we are about to trace. But there is another piece of research I need to tell you about. In January of 2021, at the 237th meeting of the American Astronomical Society, a doctoral candidate named Nick Oberg from the Captain Astronomical Institute in the Netherlands presented his findings on the long-term fate of both Voyager spacecraft. Using data from the European Space Agency's Gaia mission, which has mapped over 1 billion stars with extraordinary precision, Oberg modeled what will happen to both Voyager probes over billions of years. His team calculated star encounters, dust cloud erosion, galactic orbital oscillations, and even the effects of the eventual collision between our Milky Way and the Andromeda galaxy. His conclusion was remarkable. Both golden records, those 12-inch gold-plated copper discs carrying the sounds and images of Earth, are highly likely to survive at least partially intact for a span of over 5 billion years. 5 billion years. That is roughly the time remaining before our Sun dies. The records that Carl Sagan helped create in 1977 may outlast our star. Let us begin this journey where it should begin, with where Voyager 1 is right now, at this very moment. As of 2026, Voyager 1 is approximately 25.9 billion kilometers from Earth. That is 172 astronomical units. An astronomical unit is the distance from the Earth to the Sun. So Voyager is 172 times farther from the Sun than we are. It is traveling at 17 kilometers per second. That is 61,000 kilometers per hour. 38,000 miles per hour. To put that in perspective, a bullet from a rifle travels at about 1 kilometer per second. Voyager is moving 17 times faster than a bullet. And it has been moving at this speed, with no engine, no fuel, nothing pushing it, for almost 50 years. Here is something that will make your skin tingle. On November 18, 2026, Voyager 1 will reach a milestone that no human-made object has ever achieved. It will be exactly 1 light day from Earth. That means a radio signal traveling at the speed of light, 300,000 kilometers per second, will take a full 24 hours to travel from Earth to Voyager. If NASA sends a command to Voyager at noon on a Monday, the spacecraft will not receive it until noon on Tuesday, and the reply will not arrive back on Earth until noon on Wednesday. 2 full days for a conversation at the speed of light. And light is the fastest thing in the universe. Nothing travels faster. Yet even at that impossible speed, it takes an entire day to reach our farthest spacecraft. Now consider this. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. Voyager is at 1 light day. A light year contains 365 light days, so Voyager has covered less than 1/300th of the distance to the nearest star. After almost 50 years of travel, at 61,000 kilometers per hour, the universe is incomprehensibly vast. And this is just the beginning. What is Voyager 1 experiencing right now? What is it like out there? On August 25, 2012, Voyager 1 crossed a boundary called the heliopause. This is the point where the Sun's solar wind, that constant stream of charged particles flowing outward from our star, finally becomes too weak to push back against the pressure of interstellar space. Beyond the heliopause, you are no longer in the Sun's domain. You are in interstellar space. The space between the stars. Voyager 1 was the first human-made object to cross this boundary. The first human creation to leave the protective bubble of our star and enter the wilderness between stellar systems. And what did it find out there? Something surprising. The interstellar medium, the material between the stars, is not empty. It is filled with an extremely thin plasma of ionized hydrogen, helium, and heavier elements. Voyager measured the electron density outside the heliosphere at about 0.055 electrons per cubic centimeter. That sounds tiny. And it is. Earth's atmosphere has 10 to the 19th power molecules per cubic centimeter. Interstellar space has 0.055. The difference is staggering. But here is the paradox. The temperature of this interstellar plasma is between 30,000 and 50,000 degrees Kelvin. That sounds impossibly hot. But temperature in physics is just a measure of how fast particles are moving. When you have only a handful of particles per cubic centimeter, even if they are moving fast, they cannot transfer any meaningful heat to anything. Voyager's surface is not being heated by this plasma. In fact, Voyager is freezing. The spacecraft's temperature is determined by the cosmic microwave background radiation, which bathes all of space at a frigid 2.7 degrees above absolute zero. Voyager 1 is one of the coldest objects humanity has ever created. It is also being bombarded by cosmic rays. Galactic cosmic rays are high-energy particles, mostly protons, that have been accelerated by supernovae and other violent events throughout the galaxy. Inside the heliosphere, the Sun's magnetic field deflects many of these cosmic rays. But outside, Voyager is exposed to the full force of galactic radiation. Its instruments detected a dramatic increase in cosmic ray intensity after crossing the heliopause. This cosmic ray bombardment will continue for the rest of Voyager's journey, for billions of years. Slowly, imperceptibly, these particles will damage the spacecraft's electronics, its structure, its golden record. But the process is extraordinarily slow. Let me tell you about Voyager's power supply, because this is crucial to understanding the timeline ahead. Voyager 1 does not run on solar panels. At its distance, the Sun appears as nothing more than a bright star. Solar panels would be useless. Instead, Voyager carries 3 radioisotope thermoelectric generators, or RTGs. These devices contain plutonium-238, a radioactive isotope with a half-life of 87.7 years. As the plutonium decays, it produces heat. Thermocouples convert this heat into electricity. At launch in 1977, the RTGs produced 470 watts of electrical power. That is less than a household microwave oven. But it was enough to run all of Voyager's scientific instruments, its radio transmitter, its computers, and its heaters. But plutonium decays. Its power output drops by about 4 watts per year. By 2026, the RTGs produce only about 220 watts. Not enough to run everything. So NASA has been making heartbreaking choices. One by one, they have shut down Voyager's scientific instruments. The cameras were turned off decades ago, back in 1990, after Voyager took that famous photograph of Earth as a pale blue dot. The ultraviolet spectrometer was shut down. The plasma science instrument failed. In April of 2026, NASA shut down the low-energy charged particles instrument. Only a handful of instruments remain active, and by approximately 2036, the power will drop below the threshold needed to maintain even basic communication. The radio transmitter will go silent. The last bit of data will arrive at Earth. And then nothing. Silence, forever. But here is the critical thing to understand. When Voyager goes silent, it does not stop. The spacecraft will keep traveling at 17 kilometers per second indefinitely. No force in the universe will slow it down in any meaningful way. Newton's first law of motion tells us that an object in motion remains in motion unless acted upon by an external force. In the near vacuum of interstellar space, there is essentially no friction, no drag, no resistance. The gravitational influence of distant stars is negligible at these distances. Voyager will coast. Forever, it will become a silent, dark, cold artifact. A dead spacecraft carrying a golden record of human civilization, drifting through the cosmos long after the civilization that created it has vanished. Now let us talk about Voyager's radio signal, because this gives you a sense of the distances we are dealing with. Voyager's transmitter operates at 23 watts. 23 watts. That is less than the power of a dim light bulb, less than the power of a refrigerator light. And this tiny signal has to cross 25 billion kilometers of empty space to reach Earth. By the time it arrives, the signal has spread out over an enormous sphere. The power that reaches NASA's antenna is approximately 10 to the minus 16 watts. That number is so small it is almost incomprehensible. 10 to the minus 16 watts. For comparison, the kinetic energy of a single snowflake gently landing on your hand is about 20 billion times more powerful than the entire signal arriving from Voyager 1. NASA detects this impossibly faint whisper using the Deep Space Network, an array of enormous 70-meter radio dishes located in California, Spain, and Australia. These are among the most sensitive radio receivers ever built, and even they are straining to hear Voyager's dying signal. After 2036, even these dishes will not be enough. The signal will be too weak, and humanity will lose contact with its most distant child. Forever, let us now pause. Take a breath. Because we are about to begin the real journey. The long journey. From now until the death of our sun. And we are going to track Voyager every step of the way. But first, I need to give you a complete understanding of the sun. Our star. The engine of our solar system. Because you need to understand how it lives, how it ages, and how it will die, to truly appreciate what Voyager's journey means in that context. Our sun was born approximately 4.6 billion years ago. It formed from a collapsing cloud of hydrogen and helium gas, probably triggered by the shockwave from a nearby supernova explosion. As the cloud collapsed under its own gravity, it spun faster and faster, flattened into a disk, and the center became denser and hotter until hydrogen atoms in the core were squeezed together so tightly that they began to fuse. Hydrogen nuclei, protons, merged together to form helium nuclei, releasing enormous amounts of energy in the process. This is nuclear fusion, the same process that powers a hydrogen bomb. But in the Sun's core, it happens continuously, in a controlled balance, fusing 600 million tons of hydrogen into 596 million tons of helium every single second. The missing 4 million tons? That mass is converted directly into energy, according to Einstein's famous equation, E equals mc squared. 4 million tons of matter transformed into pure radiant energy every second. That is what lights up our sky. That is what keeps us alive. The Sun is classified as a G-type main sequence star, specifically G2V. We often call it a yellow dwarf, though in reality it appears white when seen from space. Its core temperature is 15 million degrees Celsius. Its core pressure is 265 billion atmospheres. At the surface, the temperature drops to about 5,500 degrees Celsius, and it has been burning steadily, reliably, predictably, for 4.6 billion years. Here is the crucial question. How much fuel does the Sun have left? The Sun contains enough hydrogen to sustain core fusion for a total of approximately 10 billion years. It has already burned through 4.6 billion years of that fuel. That means it has roughly 5.4 billion years of main sequence life remaining. 5.4 billion years before the hydrogen in its core runs out and the real death process begins. But the Sun is not static during this time. It is slowly getting brighter, about 1% brighter every 110 million years. This happens because as hydrogen is fused into helium in the core slowly contracts and heats up, increasing the fusion rate. Today's Sun is about 30% brighter than it was when Earth first formed. And this slow brightening has consequences. Dire consequences for Earth. But we will get to that. Let us now map out the Sun's complete life cycle, every stage, from now until its final death. Right now, the Sun is in what astronomers call the main sequence phase. This is its stable period. The hydrogen is fusing steadily in the core. The outward pressure from radiation perfectly balances the inward pull of gravity. This is called hydrostatic equilibrium. It is what keeps the Sun from collapsing or exploding. It is the most stable arrangement a star can achieve. And it will maintain this balance for another 5.4 billion years. But during this time, the Sun is slowly changing, getting hotter, getting brighter. In approximately 1 billion years from now, the Sun will be about 10% brighter than it is today. That sounds small, 10%. But it will be catastrophic for Earth. A 10% increase in solar luminosity will trigger a runaway greenhouse effect. The oceans will begin to evaporate. Water vapor is itself a greenhouse gas, which traps more heat, which evaporates more water, which traps more heat. A feedback loop. Within a few 100 million years after this threshold, all of Earth's oceans will have boiled away into space. Earth will become a dry, hellish world. Like Venus. No liquid water, no life as we know it. The atmosphere will be thick with steam and carbon dioxide. Surface temperatures could exceed 400 degrees Celsius, and the Sun will still appear normal. Still a yellow main sequence star, just a little brighter. The slow murder of Earth happens while the Sun seems perfectly healthy. It is a chilling thought. In 3.5 billion years, the Sun will be about 40% brighter than today. By this point, Earth will be completely sterilized. Not just no humans, no animals, no plants, no bacteria, no life of any kind. The surface will be too hot for any biochemistry. Earth will be a dead rock, baked by its own star. In 4.5 billion years, something dramatic will happen that has nothing to do with the Sun. Our galaxy, the Milky Way, will begin colliding with the Andromeda galaxy. These two massive spiral galaxies are currently approaching each other at 110 kilometers per second. They are separated by 2.5 million light-years. But in 4.5 billion years, they will meet. Now, galaxy collisions are not like car crashes. Stars are so far apart that almost no stars will actually hit each other. But the gravitational disruption will be enormous. Stars will be flung into new orbits. The orderly spiral structure of both galaxies will be torn apart. Over the course of 1 billion years or so, the two galaxies will merge into a single, larger elliptical galaxy that astronomers have already named Milky-Andromeda, or sometimes Milkomeda. And during this merger, some stars and objects will be ejected from the combined galaxy entirely, flung out into intergalactic space by gravitational slingshots. We will come back to this, because it has direct consequences for Voyager. Now, 5 billion years from now, this is the critical moment. The hydrogen fuel in the Sun's core is finally exhausted. After 10 billion years of steady fusion, there is no more hydrogen left in the core to burn. The core is now pure helium. And helium cannot fuse at the temperatures and pressures currently in the core. Helium fusion requires much higher temperatures, around 100 million degrees Celsius, compared to the 15 million needed for hydrogen. So, with no energy source fighting against gravity, the core begins to collapse. This is the beginning of the end. As the core collapses, it heats up, the temperature rises, and this rising temperature does something important. It ignites hydrogen fusion in a shell surrounding the inert helium core. Shell burning. This is different from the stable core burning of the main sequence. Shell burning is unstable. It produces more energy than core burning did. And that extra energy pushes the outer layers of the Sun outward. The Sun begins to expand. Over the next few 100 million years, the Sun transitions from a main sequence star to a subgiant, and then to a red giant. Its radius increases enormously. From its current size of about 700,000 kilometers, it will swell to over 100 million kilometers. Possibly 200 million. That is an increase of 100 to 200 times its current size. Its surface, now stretched over a vastly larger area, cools from 5,500 degrees to about 3,000 degrees Celsius. It glows a deep, angry red. The Sun becomes a red giant star. Its luminosity, the total energy it radiates, increases to 2,000 to 3,000 times its current brightness. Even though the surface is cooler, the sheer size of the star means it radiates enormously more total energy. Mercury is swallowed, consumed by the expanding Sun. It ceases to exist. Venus follows. Engulfed, vaporized, its entire mass absorbed into the Sun's swollen outer envelope. And Earth? This is where it gets interesting. For decades, astronomers assumed Earth would be consumed as well. But recent research has complicated the picture. As the Sun expands, it also loses mass. Stellar winds carry material from the Sun's outer layers into space. The Sun might lose as much as 30% of its mass during the red giant phase. With less mass, the Sun's gravitational pull weakens. The planet's orbits expand outward. Earth could migrate from its current orbit at 1 astronomical unit to perhaps 1.5 or even 1.7 astronomical units. The question is whether this orbital expansion happens fast enough to stay ahead of the Sun's expanding surface. Research published in 2023 and 2024 by teams using advanced stellar evolution models suggests that Earth may barely survive. It might not be engulfed. But it will be scorched. Its atmosphere will be stripped away. Its surface will be molten rock. It will be a barren, dead, unrecognizable world orbiting just outside the bloated red Sun. A ghost of what it once was. This red giant phase lasts for roughly 1 billion years in total, though the Sun spends different amounts of time at different sizes during this phase. Then comes the helium flash. Deep in the core, the collapsing helium has been getting hotter and hotter. Remember, the core cannot fuse helium until it reaches 100 million degrees. But the weight of the entire star pressing down on the core keeps heating it. And eventually, it gets there. 100 million degrees. And helium ignites. But not gently. In low-mass stars like our Sun, the helium ignition happens as a flash. A sudden, explosive ignition. The energy released in the helium flash is enormous, briefly rivaling the luminosity of an entire galaxy. But here is the strange thing. You would not see it from outside the star. The energy is absorbed by the overlying layers. The flash restructures the core, expands it slightly, and establishes a new equilibrium. Now, the Sun is burning helium in its core. Fusing 3 helium nuclei into 1 carbon nucleus through what is called the triple alpha process. And sometimes a carbon nucleus captures another helium to become oxygen. So the core is now producing carbon and oxygen. This helium burning phase, sometimes called the horizontal branch phase, is relatively stable but much shorter than the main sequence. It lasts only about 100 million years. A cosmic blink. When the helium in the core is exhausted, things get chaotic. The Sun enters what astronomers call the asymptotic giant branch, or AGB phase. Now there are 2 shells of fusion happening simultaneously, a hydrogen-burning shell and a helium-burning shell, layered around an inert core of carbon and oxygen. These double shells are deeply unstable. They undergo thermal pulses, periodic surges in fusion rate that cause the star to swell and contract rhythmically. Each pulse ejects more material into space. The Sun's mass loss accelerates dramatically. Stellar winds now carry matter away at enormous rates. The Sun is literally shedding its outer layers into space. During this AGB phase, the Sun reaches its maximum size, possibly 1.2 astronomical units in radius. That would extend beyond Earth's original orbit. Even if Earth survived the first red giant expansion, this second expansion might finally claim it. The Sun is now a pulsating, unstable, mass-losing giant, surrounded by shells and nebulae of its own expelled material. And then comes the finale, the most beautiful death in all of astrophysics, the planetary nebula. The Sun's outer layers, pushed and ejected by thermal pulses, stellar winds and radiation pressure, finally detach completely from the core. They drift outward into space as a glowing shell of gas. Meanwhile, the core is exposed, a tiny, incredibly hot, incredibly dense ball of carbon and oxygen. Its surface temperature can exceed 100,000 degrees Celsius. This exposed core blasts ultraviolet radiation outward, which ionizes the expanding gas shell, causing it to glow in spectacular colors. Oxygen glows green and blue. Hydrogen glows red. Nitrogen adds purple hues. This is a planetary nebula, one of the most visually stunning objects in the universe. But it is brief. Cosmically speaking, a planetary nebula lasts only 10,000 to 20,000 years before the gas disperses into the interstellar medium and fades from view. A beautiful but fleeting farewell, and what remains is the core. A white dwarf. The final state of our Sun. It is roughly the size of Earth, about 12,000 kilometers in diameter. But it contains approximately 60% of the Sun's original mass. Incredibly dense. A teaspoon of white dwarf material weighs about 5.5 tons. There is no fusion occurring, no energy being produced. The white dwarf shines only from residual heat. It starts incredibly hot, perhaps 100,000 degrees at the surface, and slowly cools over trillions of years. Slowly, impossibly slowly, it radiates its heat away into the void. The sun is dead. It will take longer than the current age of the universe, longer than 13.8 billion years, for the white dwarf to cool completely to a hypothetical black dwarf. As of today, the universe is not old enough for any black dwarfs to exist anywhere. Every white dwarf ever formed in the history of the cosmos is still cooling. That is the sun's story. Born from a cloud of gas, lived for 10 billion years as a stable fusion reactor, died as a red giant, planetary nebula, and finally a white dwarf. Everything between now and that final white dwarf stage takes approximately 5 to 7 billion years, depending on how you define the sun's death. If you define it as the moment fusion permanently ceases, it is approximately 6 to 6.5 billion years. If you define it as the white dwarf phase beginning, it is approximately 7 billion years. Now, let us return to Voyager, and let us trace its path through this entire timeline, year by year, century by century, millennium by millennium, era by era, until the sun draws its last breath. We start where we are. 2026. Voyager 1 is 172 astronomical units from the Sun, traveling at 17 kilometers per second relative to the Sun. It is in interstellar space, beyond the heliopause, surrounded by thin interstellar plasma and bombarded by galactic cosmic rays. Its RTGs are producing about 220 watts of power. A handful of instruments are still active. The radio transmitter is still broadcasting data back to Earth. NASA's Deep Space Network can still hear it, though the signal is impossibly faint. Voyager is awake. Alive, communicating. This is the last era in which Voyager will have any connection to humanity. Let us move forward 10 years. To 2036. The power from the RTGs has dropped to approximately 180 watts. This is below the threshold needed to maintain basic spacecraft operations and communication. NASA sends one final command. Perhaps an instruction to shut down in an orderly manner. Perhaps a farewell message. The spacecraft acknowledges. One last data packet transmits back to Earth, taking over 24 hours to arrive. And then silence. The transmitter powers down. The computers go dark. The heaters stop working. Voyager 1 has spoken its last word to humanity. But it has not stopped. It is still traveling at 17 kilometers per second. At 3.6 astronomical units per year. Nothing has changed about its trajectory. It has simply gone quiet. It is now a dark, cold, silent projectile, smaller than a school bus, carrying a golden record on its side, hurtling through interstellar space at 38,000 miles per hour. Let us think about what happens to the spacecraft physically in these first decades of silence. Without heaters, Voyager's temperature drops rapidly. Within days, it reaches equilibrium with the cosmic microwave background, about 2.7 degrees above absolute zero, minus 270.45 degrees Celsius. Everything on the spacecraft that could freeze has frozen. Any residual fluids in the hydrazine thrusters, frozen solid. The electronics, while non-functional without power, are preserved in this deep freeze. Metal does not rot. Metal does not decay in vacuum. There is no oxygen to corrode it, no water to rust it, no bacteria to decompose it. The spacecraft is now in a state of near-perfect preservation. The cold vacuum of interstellar space is the greatest preservative in the universe. The golden record is particularly well protected. It is a 12-inch disc made of copper, plated with gold. Gold is one of the most chemically inert elements. It does not react with anything you might find in interstellar space. The aluminum cover, engraved with symbolic instructions for playback, adds another layer of protection. In this vacuum, at these temperatures, the golden record will remain essentially pristine for millions of years. Its primary enemy is not chemistry, not decay, it is physics. Specifically, the impact of interstellar dust grains traveling at high relative velocities. Now let us jump ahead. 100 years from now. 2126. Voyager 1 has traveled approximately 360 more astronomical units since going silent. Its total distance from the Sun is now around 530 astronomical units. For reference, Pluto's average orbital distance is about 40 astronomical units. Voyager is 13 times farther from the Sun than Pluto. But it is still well within the gravitational domain of our solar system. The Sun's gravity extends out to roughly 100,000 astronomical units before the gravitational influence of neighboring stars becomes comparable. Voyager is nowhere near that boundary yet. The region Voyager is approaching is fascinating. It is entering the domain of scattered disk objects and the very beginnings of what might be considered the inner Oort Cloud. These are regions where occasional icy bodies exist in extremely distant orbits around the Sun. But the density of objects here is incredibly low. The chance of Voyager encountering anything, even a small rock, is essentially zero. 300 years from now. Approximately 2300. Voyager has traveled roughly 1,000 additional astronomical units since launch. It is now approaching what scientists estimate to be the inner edge of the Oort Cloud. The Oort Cloud is a theoretical but well-supported structure, a vast spherical shell of trillions of icy bodies that surrounds our solar system. Its inner edge is believed to lie at approximately 2,000 to 5,000 astronomical units from the Sun. Its outer edge extends to perhaps 100,000 astronomical units. That is nearly 2 light years. The Oort Cloud represents the true outer boundary of our Sun's gravitational domain. Voyager enters this realm. And what does it encounter? Almost nothing. Despite containing trillions of icy bodies, the Oort Cloud is staggeringly vast in volume. The average distance between objects in the Oort Cloud is estimated at billions of kilometers. Voyager could travel through the entire Oort Cloud and never come within 1,000,000 kilometers of any object. The probability of collision is so close to zero that it might as well be zero. Let us jump to 1,000 years from now. 3026, if you want to put a date on it. Voyager has now traveled roughly 3,600 astronomical units from its launch point. Adding to its starting distance when it went silent, it is approximately 3,800 AU from the Sun. It is well into the Oort Cloud now, surrounded by nothing detectable. The Sun, if you could look back, would appear as just another star. Bright, yes, the brightest star in the sky. But clearly, just a star. Not a disk, not a warm presence, just a point of light. The golden record, after 1,000 years in interstellar space, is still in essentially perfect condition. 1,000 years is nothing to gold and copper in a vacuum. The micrometeor impacts have been negligible over this time span. Perhaps a few microscopic pits on the exposed surface. Nothing that affects the encoded information. On Earth, 1,000 years from now, human civilization is unrecognizable to us. I will not speculate about what future humans might look like or achieve. That is not what this video is about. But whatever they are, Voyager is too far away and too silent for them to communicate with. It is a relic, a time capsule from a bygone era, and it is only getting started on its journey. 10,000 years from now. Voyager is approximately 36,000 AU from the Sun. It has crossed a significant fraction of the inner Oort Cloud, still surrounded by nearly perfect vacuum, still cold, still silent, still intact. For perspective on time, 10,000 years ago from our present, humanity had just invented agriculture. The last ice age was ending. Civilization as we know it did not yet exist. 10,000 years is the entire span of recorded human history and agriculture combined. And in that same span of time, Voyager will have traveled only 36,000 AU. It still has not reached the outer edge of the Oort Cloud. The solar system is enormous. 30,000 years from now. Voyager has traveled approximately 108,000 AU, just over 1.7 light-years from the Sun. It is approaching the outer edge of the Oort Cloud. It is almost free, almost beyond any gravitational allegiance to our star. At this distance, the Sun's gravitational pull on Voyager is so weak that even the subtle gravitational influence of passing stars becomes significant by comparison. And somewhere around this time, something interesting happens. Not to Voyager per se, but in Voyager's vicinity of space. A red dwarf star called Ross 248 is approaching our solar system. Ross 248 is currently about 10.3 light-years away, but it is moving toward us. In about 33,000 years, it will pass within 3.2 light-years of our Sun, making it temporarily the closest star. And around this same time period, Voyager 1 will be in the general vicinity, though still far from this star. It is not a close encounter by any meaningful standard, but it represents the first time Voyager enters a region of space where another star's influence is noticeable. 40,000 years from now. This is a milestone that NASA itself has highlighted. In approximately 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445. This star is also known by its catalog name, AC plus 793888. It is a red dwarf star currently located in the constellation Camelopardalis. Gliese 445 is itself moving toward our solar system at 119 kilometers per second, which is why the encounter happens relatively soon despite the star currently being quite distant. Now, 1.6 light-years might sound close, but it is not. 1.6 light-years is approximately 100,000 astronomical units. For comparison, the Sun to Neptune is 30 AU. 100,000 AU is an almost incomprehensible distance. If you shrunk the Sun to a grain of sand in New York City, 100,000 AU would put Gliese 445 somewhere in the suburbs of Philadelphia. Voyager will pass through that neighborhood. It will not stop. It will not be captured by the star's gravity. It is just a distant passage. Two objects, in the cosmic sense, briefly sharing the same general region of space before continuing on their separate journeys through the galaxy. And here is what strikes me about this encounter. In 40,000 years, Voyager will drift past an alien star, and it will have no idea. Its instruments will be dead, its cameras blind, its radio silent, if there were planets around Gliese 445. And if those planets harbored intelligent beings, and if those beings had extraordinarily powerful telescopes, they might be able to detect a tiny metallic object drifting through their outer system. But Voyager could never tell them hello. It carries a golden record with instructions for playback. But those instructions assume someone finds it. And finding a meter-scale object in the vastness of space is like finding a single specific grain of sand on all the beaches of Earth, multiplied by 1,000,000. 100,000 years from now. Voyager is approximately 360,000 AU from the Sun, almost 6 light-years. It has now definitively left the Oort Cloud. It is in true interstellar space. Not just the interstellar medium near our Sun, which it entered in 2012, but deep interstellar space. the space between stellar systems where no star's gravity dominates. It is a free object now, gravitationally unbound to any star, orbiting nothing but the galaxy itself. And this is where we need to shift our thinking. Because from this point forward, Voyager's journey is not a journey away from the Sun. It is a journey around the galaxy. Everything in the Milky Way, including our Sun, including Voyager, orbits the galactic center. The Sun orbits at approximately 220 kilometers per second, taking about 225 to 250 million years to complete one orbit. This is called a galactic year. Voyager 1 left the solar system at 17 kilometers per second relative to the Sun. But relative to the galactic center, its velocity is the Sun's orbital velocity plus its own escape velocity, modified by direction. Its galactic orbit is slightly different from the Sun's, slightly faster or slower depending on direction, slightly more or less inclined to the galactic plane. Over time, this small difference in galactic orbit causes Voyager and the Sun to drift apart, not in a straight line, but in a complex orbital dance around the galactic center. Like two cars on a circular racetrack that started side by side but are traveling at slightly different speeds. After a few laps, they are on opposite sides of the track. Let us jump now to 500 million years from now. 500 million years. At this point, both Voyager and the Sun have completed approximately 2 full orbits around the galactic center. But because their orbits are slightly different, they are now separated by thousands of light years. They are in completely different regions of the galaxy. If you could somehow teleport to Voyager's location and look around, the constellations would be completely unrecognizable. Every star you know, every constellation, every pattern in the sky, all of it would be different. Because you would be in a different part of the galaxy, surrounded by different stars. On Earth, 500 million years from now, the planet is still habitable. The Sun has brightened somewhat, but the really dangerous brightening is still hundreds of millions of years away. Life on Earth might still exist, though evolution will have transformed it beyond recognition. Continents will have rearranged themselves dramatically. Perhaps a new supercontinent will have formed and broken apart again. The geological and biological history of 500 million years is beyond our ability to predict in detail. Meanwhile, Voyager has been drifting through the galaxy, encountering absolutely nothing of consequence. Remember, space is empty. Stars are separated by light years. Even the interstellar medium is almost vacuum. The probability of Voyager hitting anything substantial in 500 million years is negligible. It has encountered interstellar dust. Yes, tiny grains, submicrometer in size, hitting the spacecraft at relative velocities of perhaps 10 to 50 kilometers per second. Each impact vaporizes a tiny crater in the surface. Over 500 million years, the accumulated erosion is noticeable, but not catastrophic. The outer surfaces of the spacecraft are pitted and roughened, but the golden record, partially shielded by the spacecraft body, remains largely intact. Now, 1 billion years from now. This is the time frame that Professor Avi Loeb and his student Shokhruz Kakharov at Harvard specifically modeled. Their calculation shows that within 1 billion years, Voyager reaches the opposite side of the Milky Way disk relative to the Sun. Approximately 50,000 light-years away, it has completed roughly 4 galactic orbits. The Sun has completed 4 galactic orbits too, but on a slightly different path. They are now on opposite sides of a structure 100,000 light-years across. And what is happening back at Earth? This is where the timeline becomes grim. 1 billion years from now, the Sun is 10% brighter than today. The runaway greenhouse effect has begun. Earth's oceans are evaporating. The planet's surface temperature is rising past the point where liquid water can exist. Within a few 100 million years of this point, all oceans will be gone. All surface water, gone. Earth is transitioning from a blue marble to a brown, desiccated wasteland. Life, if any remains, is retreating to deep underground reservoirs where geothermal energy provides warmth and liquid water still exists in pockets. But the golden age of Earth's surface biosphere is ending. Voyager, 50,000 light-years away, drifts on, completely oblivious. If Voyager had consciousness, it would not know its home planet was dying. It would not care. It is just a piece of metal following the laws of physics through the cosmos. 2 billion years from now. Voyager has completed roughly 8 galactic orbits. Its position relative to the Sun is constantly changing as their different orbits carry them through different regions of the galaxy. Sometimes closer together, sometimes farther apart, but always separated by thousands to tens of thousands of light years. On Earth, 2 billion years from now, the planet is increasingly hostile. The Sun is 20% brighter. Surface temperatures are extreme. The atmosphere has been transformed. Any surviving life is deep underground or gone entirely. 3 billion years from now. Approximately 12 galactic orbits for Voyager. The Sun is now about 30% brighter than today. Earth is thoroughly dead. The surface is a roasting furnace, no atmosphere to speak of. Plate tectonics may have slowed or stopped as the planet's interior cools. Earth is becoming geologically as well as biologically dead. 3.5 billion years. The Sun is roughly 40% brighter. Earth is completely sterilized. No life of any kind exists on the planet. It is a dead, baked rock orbiting a star that is slowly killing it. And now we approach the galactic merger. 4 to 4.5 billion years from now. The Milky Way and Andromeda begin their cosmic collision. These two spiral galaxies, each containing hundreds of billions of stars, begin to interact gravitationally. Tidal streams of stars are pulled outward. The spiral arms distort. Over hundreds of millions of years, the two galaxies pass through each other, swing back, pass through again, and gradually merge into a single large elliptical galaxy. During this process, gravitational interactions can fling stars and other objects out of the merged galaxy entirely. Nick Oberg's research estimated the probability that each Voyager probe would be ejected from the galaxy during this merger event. His models suggest there is a meaningful probability, perhaps 1 in 5 for one of the probes. That gravitational slingshot effects during the merger could send Voyager on a trajectory out of the galaxy and into intergalactic space. If Voyager is ejected from the galaxy, its fate changes dramatically. Intergalactic space is even emptier than interstellar space. Dust density drops to nearly zero. Cosmic ray flux decreases. The golden record would be even better preserved, as the primary source of erosion, interstellar dust impacts, would be dramatically reduced. An ejected Voyager could drift for trillions upon trillions of years with virtually no degradation beyond the slow nuclear decay of its own atoms. But let us assume Voyager is not ejected. Let us assume it remains within the merged galaxy, now called Milky-Andromeda. Its galactic orbit has been significantly perturbed by the merger. It is no longer on a predictable path. The gravitational chaos of the merger has sent it on a new, random orbit through the merged galaxy. It could be closer to the galactic center or farther away. It could be above or below the galactic plane. Its orbit has been randomized. And now, we arrive at the critical moment. 5 billion years from now. The Sun's core hydrogen is exhausted. The main sequence is ending. The death process begins. Where is Voyager 1 at this moment?
Greetings from the inhabitants of Earth.
Hello, we send our greetings.